electromagnetic fields, to treat materials, to change materials, the properties of materials. That is, on one hand, it is via the liquid phase, by melting and then solidification or crystallization. And on the other hand, it is by heat treatment, for example, or by other treatments. And I will show you some examples about these technologies. Some technologies are quite old. For example, induction melting, it is well known since 80, 90 years, and used in industry, but with increasing factor. But some are very new, some are really new, and very innovative. And this is a challenge for the, let's say, for the future. So, EPM, I call it EPM, yes, electromagnetic processing of materials technologies have special properties. They allow heat treatment, flow treatment, melt flow treatment, and force treatment. You know, electromagnetic fields, described by Maxwell's equations, they can generate heat, if you have currents in the material, we call it Joule heat, and on the other hand, they can generate forces. The main part are Lorentz forces, and these forces can drive liquid melts, for example. A big advantage is we have a contactless treatment, and we are free of the choice of atmosphere. So we can work in vacuum, or in inert atmosphere. And as typical for electromagnetic processes, is that we have a direct processing within the material. And this offers a lot of advantages as described here. I hope everybody can see it here. We can realize a very high power density. We can heat very fast. You will see it in one example. We have no limitation of temperature. We can generate each temperature we want. Also one example I have. And we can realize a combined application of heat, steering, and force treatment. So altogether, what can be done with electromagnetic processing. We have a precise time-dependent and local processing. We can concentrate on some areas. We can produce materials with very high purity. This, on one hand, this depends on the atmosphere we can use, on vacuum, for example. And also we can produce high quality. We have a high flexibility, high productivity, I also will show you, and a high level of integration in process lines. So altogether, besides the classical applications, it enables new technologies, and I will show you some examples in the following. I start with the more classical applications, and first is the use of EPM in metal processing. Very classical, of course, is induction melting of metals. Then I come to the heat treatment of metals, also more or less quite old, but today with new aspects. And electromagnetic segregation. This is a quite new application of EPM, and I have a very nice example. So induction melting. Induction melting is used in the industry since many, many years, Main applications are melting of iron, gray iron, but also steel today, copper, aluminium, zinc, and today also increasing is magnesia, So, classical applications, but the aim to investigate this process and to optimize this process is still today. So, what is the main direction of induction heating? Induction heating for melting, it is a strong mixing and homogenization of the melt, to get a homogeneous melt alloy, for example. Also the homogenization of the temperature to avoid overheating, because it can damage the material. And sometimes also a sufficient superheating of the melt to be able to cast it. We need sometimes an intensive steering at the melt surface, for example, to melt in small size scrap or carbon, yeah, for gray iron. On the other hand, we have to control the steering not to be too strong in steering to avoid erosion and clogging, because the melt normally is in a ceramic lining, in a ceramic crucible, and it should not be destroyed. We should also avoid melt instabilities, yeah, that the melt is a liquid, yeah, that it is coming out due to forces, splashing or pinching, we call it. And sometimes we need an extensive steering for cleaning of the melt. One very actual example is the zinc removing from the steel, which comes from the car industry, yeah? From the scrap of the car industry, because car industry use zinc, and zinc has to be removed. Yeah? So we do a lot to investigate this behavior of the induction furnaces, and also one direction, of course, one very important is to simulate, to use numerical simulation to investigate this. And if you do this with a very, let's say, simple installation like an induction furnace, you have a very complex system, of course, which you have to investigate. No? Because the main thing is you use electromagnetic fields. That means you have to investigate the magnetic field. The magnetic field generates, of course, Joule heat. That means you have a temperature field here. But also, as I said, electromagnetic fields generates Lorentz forces. That means you have a velocity field. You will see it in the next slides. And also it deforms the shape of the melt, and we have a meniscus shape. You will also see it in the slides. In some applications, like cold crucible, I will show you we have a skull formation. And of course, we have an alloy composition due to the mixing. Yeah? All this you have to take into account, and as you can see, more or less everything is coupled. Yeah? So, in principle, for melting, induction melting, we have two different devices. That is an induction crucible furnace. That is the main part today for melting of iron and steel, yeah, with very high power, up to 40 megawatt today. Yeah. And we have the channel furnace, which is mainly used for holding and pouring in iron industry, but also used for melting in non-ferrous, copper, zinc, aluminium industry. Yeah. I will show you now some examples of the crucible furnace. Here you see only the cross-section of a crucible furnace, which was simulated by so-called 3D large eddy simulation to simulate the melt flow. It is a real industrial furnace at 12-ton gray iron furnace. Power is 9.3 megawatt. The frequency, which is used, 230 hertz. The diameter is 1 meter 20. Yeah, so in total that means 12 tons. And here you see the simulation of the melt flow in the cross section. It is a transient simulation. It starts very homogeneous. Yeah, you have a typical flows which are going here, yeah, in that direction. But after some certain time, around 10 seconds, then it becomes more or less chaotic. Yeah, and this chaotic, you can imagine that it very strongly mixes the melt. Yeah, and therefore you have a very homogeneous melt distribution. So. Next simulation shows the middle line, yeah, and also in the beginning this is quite quiet, but after again 10 seconds, here you can see the time is running. After around 12 seconds, it starts to move, yes, up and down, and this is also the reason for the strong mixing. And here you see now a view to the top of the melt. Yeah, the melt is coming out from the center. No, sorry, out from the center, and then going to the crucible side. And here you see also the strong mixing from the top of this furnace. So better you can see it maybe in this case. This is another model for a furnace. It has 6 tons. 6 tons, it is not written here, 6 megawatt, a little bit smaller furnace. And here you see also the meniscus shape, which I told you, yes, due to the Lorentz forces. Yeah, the melt flow is deformed by Lorentz forces. They press to the melt, and because it is liquid, of course, yeah, it changed the shape. Yeah, and in the next slide, you see here also, this is more realistic, yeah, the melt flow inside such a crucible, inside such a melt of an induction crucible furnace. So this investigations with a very complex simulation tools helps us to investigate, to optimize this process, even if this general process is already 80, 90 years old, but today there are still some optimizations needed. So the next example I will show you is a cold crucible. Cold crucible technique is shown here. Now maybe I go first to this slide. This is a typical principle of a cold crucible. In classical crucibles, which I showed before, we have a ceramic crucible, yeah, because this is a conventional type, ceramic, maybe SiO2 or Al2O3, yeah, crucible. Of course, you can imagine that if you melt some materials inside the ceramic with a strong mixing, you have sometimes some kind of erosion from the ceramic. Yeah? So some parts of the ceramic will go to the melt. Okay, if you maybe cast some engine blocks for your car with it, nobody takes care of some small particles in the casted part. But if you, for example, want to cast turbine blades, yeah, and there is one ceramic particle in, nobody accepts this. Yeah? So for this kind of materials, you need another device. And one of the other devices is the so-called cold crucible. What is a cold crucible? Here you have a crucible which is made of metal, typically copper or copper alloy, which is water-cooled. Normally it makes no sense because you want to heat the melt inside. Yeah? But it makes sense because due to the strong water cooling of the crucible, you have no contamination, yeah, with the melt. Yeah? So you have no some impurities coming to the melt. You have no treatment of the crucible. So from this point of view, it makes a big sense to use it, and it is well established meanwhile also in industry. Due to the strong electromagnetic forces, you have a very strong meniscus. So the shape, the meniscus, the surface of the melt is strongly deformed, and therefore you have no thermal contact here on the side walls with the water-cooled crucible. So to reduce, this is an advantage to reduce the losses. Yeah? And the contact is only in the bottom part. So this, I go shortly back, this cold crucible was developed in the 90s. I have to say, originally it is an invention of Russian colleagues in Moscow from the old Electroheat Institute Veneto. But the German company, it's written here, ALD, take over some patents and then developed this in the 90s to an industrial scale application. And our institute has a lot of cooperation projects at that time together with some companies here. For example, you know very well these names here, automotive car industries. TRW is a producer of these valves here. Yeah? So there was a big investigation to make this process for industrial use. And the main aim was to melt and to cast in one step, yeah? To reduce costs. To use it also for, let's say, daily parts in automotive industry. And some results I will show you here. Here's, okay, again, described a little bit the principle of the cold crucible. Of course, it has to be slitted, yeah, because if it is made of metal and you have here the induction coil, If it is not slitted, of course, you have a kind of Faraday ring, yeah, and no electromagnetic field goes in. But due to the slits here, magnetic field goes in. It's a kind of transformation by these segments here. And so the magnetic field goes in and then melt the material. You have an intensive melt stirring. You have this free surface I told you already. Everything is water-cooled, the segments, the bottom. And of course, you have a lot of heat losses by radiation, yeah, here. And of course, by conduction here on the bottom. And also radiation here on the top. Here you have a view to such a real furnace. You see here again the segments. Here the slits, very thin slits, closed a little bit by ceramic. Yeah, but this ceramic is strongly water cooled, so there is no big problem. And here you see the meniscus of the melt inside. In the 90s, this was used to melt titanium aluminum. Yeah. A very nice material because it is has a strength like steel. It has a temperature resistance like steel, but it has only half weight of steel. Yeah? Therefore, it can be used for very light workpieces. But the problem is you cannot melt this in classical ceramic crucibles because it will destroy your crucible in a short time. And of course, also, as I told you, impurities will come to the melt. So therefore, the cold crucible was used for melting, and still today for melting titanium aluminum, but also pure titanium and other materials. You can melt alloying, overheating, and casting in one process. This is very important because due to the strong mixing, yeah, the titanium aluminum means a part of titanium and a part of aluminum, roughly 50-50. Yeah? So, and you have to mix this, yeah? And because due to the strong stirring, you can do this mixing, this alloying, we call it, yeah, inside the crucible, yeah? And then you can melt it finally and then immediately cast it. So in one process, you can do everything with this kind of melting furnace. So it's very convenient to use this cold crucible technique. You have a good homogenization due to electromagnetic stirring. And the only one point, critical point, is overheating. Yeah? You need always for casting a certain overheating because if you have a mold, yeah, a form, call it mold, yeah, and you cast in your liquid metal, of course this mold is cold, yeah, it will immediately solidify, sometimes too fast. Yeah? So you need a certain overheating, higher temperature than melting point, yeah, to give the melt, the liquid melt, some time to solidify, to flow everywhere. Yeah? And so we need this overheating. And this is a little bit problem because if you look to the principle, of course, here you have contact with a water-cooled bottom, and here you, of course have solidified material. Yeah? We call it skull. Yeah? And all overheating in the melt has to say that we need some temperature gradient here because the solidified bottom area, yeah, and the overheating. So we need this temperature gradient inside the melt. But due to the strong stirring, yeah, you can imagine that we reduce this temperature gradient. Yeah? Strong stirring means homogenization. Yeah? And this is a little bit critical point. And this was one main point for investigation in our institute due to the control of melt flow to increase this overheating. Here you see a view to our installation we have in our institute. This is a vessel, vacuum vessel. Here you see now the cold crucible. Here is a coil. This can be tilted, yeah, and then used for casting. Here's a sketch. Again, here's a cold crucible system. Here is a mold, yeah. It's rotating, yeah, and then it is casted inside the mold. And then we generate, in this case here, this valves, yeah, for the car industry. The installation has a power of 300 kilowatt. Frequency is 10 kilohertz. And we can melt inside this crucible here 4 to 7 kilogram of titanium aluminum. So, and the first products here which came out are shown here. Directly after casting, you get this, we call it casting tree. Yeah? You see here already the valves, 12 valves in one level, and totally it was 3 levels, 36 valves. After mechanical treatment, it looks like this here. And then after use, yeah, it was used in a real car. Well, yeah, it looks quite good, yeah, typical for such valves. So these valves were tested by BMW, and they fulfilled all tests. Yeah. So this was the investigations in the 90s. After 2000, we continued this work for casting of turbine blades, turbocharger wheels, yeah, for your car, yeah, also to reduce the weight, that the turbocharger wheel comes faster to speed, yeah, everything to, yes, let's say, to decrease the fuel consumption of our cars, and of course to increase also the power, yeah, of cars. So yes, here is summarized what at that time was the topics for optimization and also the potentials. Yeah. So the main point is the overheating, as I explained already, to maximize it. Of course, you can imagine that the efficiency, the energy efficiency of such installations is not very high. That is always a critical point. But in principle, there is no better installation or device which can melt it with a better efficiency, so it is accepted. But nevertheless, of course, there are still some investigations to improve the total efficiency and to reduce the energy consumption. Then, of course, the control of the melt, composition of the steering, of the skull formation, and of course also to improve the reliability, reproducibility, and the stable melting process. So there's still a lot of work to do. It is not at the end of the investigation, but we see that it has a good future. Here you see finally the melt flow in such melt in the cold crucible. You see very intensive, yeah, more intensive than in the conventional furnaces, as I have shown before. Here you have one small vortex downstairs here. Or yes, one vortex. Yeah, you can imagine this is a kind of ring here, yeah, round. So one vortex here, yeah, and a little bit smoother and wider here, which pushes the melt to the top here. Yeah. And the next shows the temperature distribution. You see where the red is the high temperature, of course. Here you see the scale. The main heat is generated here, but it is a strong mixing. And of course, here on the bottom, you see that it is water-cooled due to the water-cooled bottom. And this is this is the aim of superheating of the melt. You see that in the top part, of course, it is quite superheated, yeah. But in this case, it was 40 degrees, 40 Kelvin. The aim is to double it, to bring it to 80, 60 at least, or 80 Kelvin. But today, this is also possible. So this was about the cold crucible technique. And now I want to show you a little bit about the principle of electromagnetic induced segregation. I will explain what it means. We call it shortly ICE. Yeah? It is similar to the German ice cream, yeah, but it doesn't mean, of course, different. Electromagnetic induced segregation. So here's shortly explained what the aim is. The direction in this special research project was the casting of these engine blocks made of aluminum, yeah, for strong cars. This was from BMW, one engine block, but the same is from Volkswagen, for example, or Daimler. So if, of course, for these engine blocks, you use aluminum, yeah, not iron, because it reduces the weight of your engine. But of course, it's clear that for aluminium, it's not a strong material. You have to improve the strength here in the inner side of the cylinders, yeah, for the mechanical treatment against the pistols. Yeah. So there are different solutions to do this. Yeah. And one solution is that is using BMW is using it. They use a special alloy which contains silicon. And it contains so much silicon that after solidification, the silicon falls out. It is no more dissolved in the aluminium. Yeah? So you really have then finally pieces of silicon inside the aluminium, the solidified aluminium. Yeah? And you can imagine silicon is very hard material. Yeah? Not like diamond, but close to diamond. Yeah? So it is increasing, of course, the strength here against the wear. So this is a classical, or not classical, but this is a standard procedure which BMW use it for their this kind of engine blocks. But it has one disadvantage. Yeah? It has one disadvantage because you need very high participation of silicon, roughly 17 to 18%, and this makes this final solidified block very critical against stresses. Yeah, so it can create cracks, yeah, inside the blocks. It makes it difficult to mechanical treat, yeah, because always you have the silicon particles. So one idea was coming up, very interesting idea, to concentrate these silicon particles only on the surface of these cylinders. Yeah? To concentrate these particles, then of course you need in general, in average, less silicon, yeah? Because only here you need it. So in general you need not 18, 19%, maybe 15 or 14. And this is much more convenient, yeah. But how to concentrate? Yeah, yeah. But there is, of course, one effect of electromagnetic fields are the Lorentz forces. Yeah. So the Lorentz forces act on materials which are conductive, electrically conductive. So it means if you, during the melting of the material, you use an inductor like this one. The inductor generates Lorentz forces, which presses away the aluminium. Yeah, Lorentz forces always tends to press away from the coil. So it presses away the aluminium, liquid aluminium. But silicon is a low conductive material, so Lorentz forces are very small, nearly zero. Yeah. So what inside the liquid happens? The aluminium is pressed away, but of course there can be no hole, yeah, because it's a liquid. The silicon is going to the surface. Yeah. This is an effect very well known, of course, in EPM. It is called purification, yeah, or segregation. Yeah. Yeah. So you can really purify materials by using electromagnetic fields, then all impurities, which are normally lower conductive, comes to the surface. Yeah? So, and this is used here. And there was some theoretical investigations before. It shows if you use this during the solidification phase, yes, you melt the material, yeah, the aluminium material, then you cast it to the casting mold where you have the shape inside. And if during solidification you let electromagnetic forces treat this solidification, then you get this shape of the silicon concentration. Here is a surface on the left side. Of course, normally to solidify you need some cooling. Yeah? So classically you have inside these cylinders, you have normally a sand mold made of sand, yeah, pressed together, of course, but inside these cylinders, you have a water-cooled cylinders, yeah, normal steels, stainless steel cylinders, water-cooled. So, and if the melt, of course, comes to the water-cooled cylinders during solidification, it immediately is solidifying. So you cannot realize any movement of the silicon particles. But the zone behind, which is not immediately solidified, there this movement can start, yeah, due to the Lorentz forces. You have a concentration of silicon. Then, of course, these silicon particles has to come somewhere, and there are now some holes. Yeah, this is this zone here, and this is then this not influenced zone. So this is a typical, at least from the theoretical point, typical zone. Yeah, directly at the surface, no treatment. Then a concentration here, then a depletion here, and then no influence. And the theory said, okay, after casting, you have to mechanical treat. You take away this surface part here. Yeah? You have to mechanically make exact the diameter. So then, after treatment, you are with your final surface just here, and there you have a high concentration of silicon. And the aim was, of course, to show that it works. Therefore, our task in this project was then to realize such inductor system. Yeah? And then together with some casting institutes in Aachen to realize experiments, and then finally really to cast such engine block. And all was done. Here you see the inductor system, a little bit more in detail. Yeah. So we have to imagine here we have let's say, a steel form which is similar to the old one, to the classical one, but the wall was reduced, yeah, because the magnetic fields have to pass the wall. And normally it is also like a Faraday ring, yeah, but if it's stainless steel, the electromagnetic penetration depth is quite big, yeah. So a big part of the electromagnetic field goes through. This is used line frequency, 50 hertz, so very low frequency. So the penetration depth was roughly 60 millimeters, and the thickness of the wall was 10 millimeters. So nearly 80% goes through the wall. So here is a melt. Yeah, in this case only one small part, yeah, of the melt. So then you can realize, hopefully, here is a coil. Yeah, cylindrical coil, and inside the coil is a magnetic core to guide the magnetic field. So that means you have magnetic field is concentrated here in the center, and then goes through the form here, inside the melt, and then close here, and the same, of course, on the other side as the symmetrical. So we have done a simulation of flux density, yeah, and you see, of course, to check, yeah, how much flux comes still to the melt. But you see here it's big. Of course, you have some end effects here, and also some top effects, which has to be investigated. The flux density was not very high, yeah, 124 millitesla. Quite low, but enough to realize this effect. And here you have the power density. Of course, power density also was important, because if the power density is too high, what means power density? That means heat. If the heat is too high, you cannot solidify. You always keep the temperature. So the Lorentz forces should be low. No, it should be high, sorry. The Lorentz forces should be high, but the power density, the Joule heat, should be low. Yeah, this was a clear aim. But there's a clear rule, clear dependence from frequency. Always in such applications for low frequency, the Lorentz forces are high, and the Joule heat is low. For high frequency, Lorentz forces are very small, and the heat is high. Yeah? So for really heating, you need high frequency. For steering, you always need low frequencies. This is a general rule. And therefore, here 50 Hertz was used because it was, of course, also the simplest way. And so the losses here, you see, was 500 watt only. And this is quite low for induction heating, typically. So it was tested then in a test installation, which is our partner in Aachen, what the Casting Institute has installed. And you see here, the power and the electrical values are not very high, of course. 2,000 amps for induction is nothing, 25 volts, and the total power loss is 4 kilowatt. And this is here it was 200 millitesla used. That was finally the best value. So all was in good shape. And here you see then again in the test installation in Aachen, this kind of test cylinder was casted. And finally at the company BMW, and final engine block was casted. And the results are shown here. Here you see the distribution of silicon particles, here a little bit bigger scale, inside the aluminum, and this is without electromagnetic segregation, yeah? So more or less homogeneous. And you see here now the structure with the use of ice, yeah? Concentration here of particles, here is the surface, yeah? On the surface, and here also. And this was done coming out from the test installation. Yeah, this was in Aachen. This is a casting institute in Aachen, and this was an industrial partner. He showed similar results. Yeah, and finally, you can see here the final structure after mechanical treatment of the surface. Here is the surface again of the cylinder, and here you see this enrichment zone, yeah, where we want the concentration. So really it works. Then here is the depletion zone. Here's nearly no silicon particles, and here is the normal eutectic region, yeah, with the original alloy. So really we could realize this enrichment zone at the surface. Yeah. And this, of course, this principle is not only interesting for these casting blocks, it's also is interesting for other parts. We called it to generate graded materials, yeah? Materials with a gradient in material properties. Yeah? So, and this will be done in future, I guess, also for other applications, not only here. So, okay, this was everything, let's say, concerning liquid materials, liquid metals, I have to say. I'll come back to liquid oxides and glasses later, but everything, all treatments was here of metals via the liquid phase. Now I'm coming to induction heat treatment, and this is a typical name for non-liquid treatment only by heat. Yeah? And one major application is the so-called induction surface hardening. Yeah? Induction surface hardening is well used in industry since many years. Typical, for example, is this crankshaft, yeah, where the crankshaft in the car, you know, yeah, the main part, yeah, moving the pistons, yeah, and of course the crankshaft has different bearing areas, yeah. For every piston, of course, there is one bearing, and the whole axle have to be laid in and rotated in bearings. So typically for a 4-cylinder car, you have 9 bearing areas, yeah, 4 pistons and 5 positions where the crankshaft itself is laying. So this is a classical application of induction surface hardening used since 25 years already. But there is an increasing demand of other materials, other workpieces, because the background is very simple. It's the following. The typical hardening process for such workpieces like a lot of workpieces in your automatic gears of cars. Yeah, there are, I don't know, 1,000 particles which has to be hardened. The typical application is you put it to a furnace, big furnace, then via a diffusion process, yeah, you bring in carbon into your pieces, yeah, from the surface. This takes high temperature, 1,000 degrees roughly. It takes time, 24, 48 hours, 1 day, 2 days, yeah, and then the diffusion process is finished, and then you take all parts out of your furnace, and then you can use them. The total period for doing this process is 1 week to 2 weeks, because you have to handle it, you have to treat it, and so on. And of course, you can imagine today in just-in-time production, yeah, 2 weeks is like a big break, yeah, in production. So I go a little bit further, and then I come back. And then if you show somebody that you can heat this part, like on the left-hand side, in 1.3 seconds, yeah, heating and then quenching, cooling, yeah. Or here it's only heating in 350 milliseconds. Yeah, you see, now shock, now and then quench. If quenching would be, it would be hardened. You can imagine if somebody looks to this process and say, the result is the same like in the 2 weeks or 1 or 2 weeks treatment, yeah, I want to have this process because I can directly integrate it into my production line. Yeah. So, but the question is, of course, you see already this, this piece here, it's a warm gear, it is quite complex. Can it really be hardened, yeah, on the surface, yes, comparably to a treatment furnace, yeah? Because in the treatment furnace, diffusion always starts from the surface. It does not matter which geometry your workpiece has, always from the surface starts the diffusion. And it's only a question of time, how deep the diffusion goes, how deep the hardening zone goes. But for induction, of course, you have to guide the currents, yeah, that it really heats your workpiece where it should be heated and where it should be hardened. So I go back. So therefore, no, that was opposite direction. Therefore, today the aim is to harden more and more pieces by induction. Yeah? What means induction hardening? We have to heat up the workpiece up to 900 degrees centigrade very fast, and then to cool it down also very fast. Yeah? We have to heat it only on the surface because we call it surface hardening. The depth normally is between 0.5 and 1 millimeter. Yeah? So, and we have, of course, we know, you are more or less electrical engineers as I know, there is a penetration depth, electromagnetic penetration depth, yeah? And the heat is only generated inside the penetration depth, and you can control penetration depth by frequency, by the frequency. Yeah? So the frequency is the main factor here to control how deep the material have to be hardened. So, okay, here's a short introduction to the topic. Of course, induction surface hardening improves the quality of the mechanical devices because the surface will become harder, stronger. The advantages is high power densities, very fast heating, as I explained you and showed you. You can integrate it into production lines. You can make a selective heating. If you put your part inside a furnace, it will be hardened all from the surface. Yeah? But if you need it only in some area, some location, it's not possible. Therefore, induction hardening, of course, can realize it only in the selected area. And this means you have less deformation. Yeah? This is a big problem. If you go to this treatment furnaces, because your parts have to be heated everywhere up to 1000 degrees centigrade and then cool down. But this means that you have normally a strong deformation, not a strong, but quite strong deformation. And this has to be finally corrected, yeah, by, again, deformation, mechanical deformation, or by mechanical tooling afterwards again. Yeah? So, and if you use induction hardening, the deformation is much less, and this is also one big advantage besides a very short heating time, process time. But as usual, yeah, if more parts should be hardened, also complex structures must be hardened, like this worm gear I showed you already. And the problem is with traditional experimental investigations, it's quite difficult. Yeah? Of course, people have knowledge how to make the inductor, but it is, let's say, for not experienced people, it's very difficult. Therefore, we have partly very high costs for long development times, and sometimes also the results are not always optimal. So therefore, we try to use 3D modeling of the transient heating and today also the hardening process, yeah, to simulate this and then to better to optimize it, to solve new hardening tasks, to investigate the inductor geometry and the hardening parameters, frequency, heating time, and power, and so on, to improve the process. And one example I want to show here is the hardening of such worm gear. Yeah, we call it worm gear. It's for a gear for low speed, yeah, which is used everywhere today in your car to open the windows, for example, yeah, or to move the seats if you have a electric seats movement. So everywhere, bigger ones for steering, yeah, in bakeries or something like that. So the question was, is it possible to harden this also by induction? Yeah? Because it could improve the productivity and lower the costs and so on. So first we made, it's covered here a little bit, we have chosen a typical inductor, call it line inductor. You see here, it has two main parts. It's a kind of linear inductor here, which then it is heating the sidewalls here. I go first again, it's better to, you see here the worm gear is rotating, yeah? And the inductor, this linear part of the inductor generates a current on this side, yeah, and a current on the other side. But due to rotating, of course, this current or the heat which is generated is just distributed over the whole circumstances. So first we created the model. It's not shown here. I forgot this slide here. Created the model of this inductor. We made a cross section here. Then we reduced this worm gear to a half teeth only, and the result was then after investigation. Here you see the temperature profile. You see here, this is a half teeth. Yeah, you can imagine if you have the downside symmetrical, then you have a whole teeth, and then if you double it or 3 times, then you have the whole gear. So, and we showed that with a single frequency, which is typically used for hardening, we were not able to harden it on the surface. Of course, the aim was this is a cut, of course, only. The surface is here, yeah, of the tooth. The aim was to harden it very homogeneous over this surface. Yeah. And you see here, if you use low frequency, 20 kilohertz, you have only a hardening inside. If you use 100 kilohertz, you have a hardening here on the top of the tooth, yeah, but not inside. And then compromise was 40 kilohertz, but also not homogeneous. Yeah. So this was no chance to make it, as we call it, contour hardening, yeah, hardening on the whole contour, on the whole surface. Therefore, we investigated a new task, and this is so-called dual frequency. Dual frequency, what does it mean? Okay, I shortly go back. You see here, if you use high frequency, you heat the tip, yeah? If you use low frequency, you heat the bottom area, the foot area. So the idea is if you can combine this, yeah, then with both frequencies, then you have a homogeneous heating. And this is the idea. You need high frequency. HF stands for high frequency. In English, typically radio frequency, RF, yeah. But here in induction, H frequency is used also in English language. High frequency mainly hits the tip of the tooth. Main frequency, the space between the teeth, yeah, so the bottom parts. And the superposition should lead to a more or less homogeneous contour hardening. There are some special techniques. You can use high and medium frequency seriously, yeah. First medium frequency, and then high. But there are also some solutions and also some patents, but they are finished now, to use it simultaneously. Yeah? Simultaneously, of course, and this is the so-called SDF technique, simultaneous dual frequency technique. Of course, simultaneously is better, yeah? But it generates some electrical problems, yeah? Because you know the inductivity or the reactance, yeah, of an induction circuit is linear to the frequency, yes? Omega times L likes inductivity. Yeah? So if the coil is the same for both frequencies, yeah, it's clear for the high frequency, the reactance is much higher than for the low frequency. That means finally for the same power, the high frequency needs much more voltage than the low frequency. Yeah? But this is, of course, this is solved. This is done by capacitive and transformer coupling. Yeah? This was the patents, but they are, as I told, they are finished now. Everybody can use it. So, and then you can change, of course, the rate or the ratio of the medium to high frequency to optimize the ratio and to optimize the heating. I will show you. So we implemented this in our numerical model. Was without big problems, and the typical frequencies for medium is 12 to 20 kilohertz, and for high is 150 to 300 kilohertz. And here you see the results now. The parameter here is a participation of high frequency. You see 30% high frequency, 70% medium. Here it is 40-60, 50-50. And after our after our simulation, we found out for this application that 50-50 gave the best results. You see here now, very close to the contour of the tooth, you have this hardened, this heating zone. I have to speak. This is temperatures, yeah, the heating zone, and classical, of course, for the hardening is 850 to 900 degrees, which you need. So this is more or less the curve here of between the red and the orange color. Yeah, this is the line of 900 degrees centigrade, and you see this is more or less close to the contour, a little bit thicker here, but this is not bad. So this was really the aim of this and the good results of this simulation. This you know already. So we we realized it then in two applications. One application is on the left side in Berlin. Sorry. Left side was in Berlin. Company Steremat. They were experienced in induction hardening, and they had such converter, but the power was limited. As you can see here, 25 kilowatt, 150 in total, and therefore the heating time was quite high. And then we asked another company, and they had a generator which has 600 kilowatt, 400 medium frequency, 200 high frequency. And with that, we could realize the heating process in a shorter time, and this was more effective than the left process. So finally, we realized this on the right-hand side. And of course, we made some experimental investigations. And for hardening, it's very easy. You have to use acid to show the hardening zone. You cut your piece, yeah, and then you put it to acid, and then it's clearly shown where is the hardening zone. And here you see the teeth, no? And of course, you can see here that very similar to the simulation, of course. The hardening zone is a little bit deeper here on the tip, a little bit smaller in the bottom part. And this was investigated then a little bit more in detail. Now you see on the left-hand side, this is a simulation. This is the line of 850 degrees centigrade. Yeah. And here on the right-hand side is a hardening profile. And you can see this is very similar. Only here is a little bit not so clear line for hardening. Now today it's also clear why. And at that time, this was already 5 years ago or 6, 7 years ago, we could say that we have a good agreement between the simulated temperature and the final hardening profile. So that means that the final hardening profile can be excellently predicted by numerical simulation by the temperature distribution. Yeah? At that time, of course, the hardening profile could not be simulated. No? That means the material conversion. And there we were proud, at that time we were proud that we could say, okay, if you investigate only the temperature profile, you can say already something about the hardening profile. Today we know that it's true for such applications where the hardening depth is very small, but for larger hardening depths, yeah, here it was 0.5 millimeter, like for some millimeters it does not fit so well because the cooling is then less effective inside the material, and therefore today we can also realize the simulation of the hardening profile of the material conversion, at least with some approximative methods. Yeah? It's not so exact like temperature and electromagnetic simulation. So you see this is also one example of electromagnetic processing of materials here in the area of solid materials, only by heat, by exploding heat very fast to the material and then to change the material properties, like in this hardening profile. Okay, so the next example I have here is very modern. It is deals with laser treatment. Yeah? Laser treatment used, you know very well, in a lot of applications for cutting, laser cutting. Yeah? This is well established already, but also in laser welding and other treatments. It is already developed the last years. So, but the laser beam welding or surface remolding leads to very high temperature gradients. Yeah? The intensity of the laser is very high, of course, you know, and very concentrated, focused. Yeah? And therefore, we get very high temperature gradients and therefore thermal mechanical stresses in the workpiece. Yeah? This is beside all, let's say, advantages of laser treatment, the small disadvantage. Another disadvantage is that laser energy is very expensive, of course, and limited. Yeah, power is limited. So the aim or the solution here is to reduce the temperature gradients in the workpiece by the combination of laser with induction heating. Yeah? Induction heating you can control. It is not so much focused. Yeah? And then you can bring more heat into the workpiece, into the area where you are welding, and it creates less thermal stresses. Yeah? So the applications are welding of high alloy steels, which tends to crack. Yeah? Crack-free welding of hardening steels and hardening of complicated shape workpieces. Here's a general sketch here, yeah, laser welding and then treatment by inductor, but this somebody has drawn, which was not very familiar with induction heating, so it's not so easy like described here. It was only for advertisement. Yeah? So, some short words, laser applications in automotive industry. Today, here you see, it's an example of Volkswagen, yes, how many percentage, how many meters are welded by laser. And today, what we have, Golf 6 or 7 already, no? Yeah. This was already 5. Yeah? Already nearly 100 meters were welded by laser. Yeah? Because it gives a lot of advantages compared to classical welding of carrosseries, yes? Less mechanical treatment, tooling afterwards, and better surfaces, and no problems with the lacquer and so on. So, but as I told you, we have then this high temperature gradients, high thermal stresses, and therefore we have carried out a lot of research projects the last 8 to 10 years, together with laser experts, with our Laser Institute in Hanover, to investigate this and to realize this combination. Yeah? And therefore, we developed a new simulation tool to combine laser and induction, also sometimes arc welding, yeah, for thicker strips. We call it hybrid method. Yeah? So here we have this, it's a typical line inductor, which of course heats the seam, and this is the laser. Yeah? In reality, you see here, this is again the inductor, and this is the laser. Yeah? And you can use the heating before the laser welding or after the laser welding. Yeah? Both is possible. We have investigated both. Now we have realized then a simulation model, take into account induction heating, what we know, of course, very well, but also take into account the laser heating. So therefore, we had to choose for the implementation of the laser or also the arc heating inside the seam. Yeah, we had to investigate the sources where the laser is generating the heat sources. Yeah, but our laser colleagues, of course, they had laser experts. They had some experience with that, and they gave us their information and data. So we implemented this in our model, and so we then could really simulate the whole process. And here you see one diagram over time. Yeah, the workpiece, the seam is coming in, then it's heated by induction, and you see here up to around 900 degrees. Then we have a small gap, as you could see, between the inductor and the laser. Yeah, you need a certain gap because otherwise you are influencing the laser by electromagnetic fields, by Lorentz forces, and also the laser can damage your inductor, so you need a little bit space. And in this space, of course, you have a cooling down, and then the laser comes and bring it up to welding more than 600 degrees centigrade, and then you have the cooling side here. And this cooling side is the important thing because the time between 800 degrees, you see here 800, and 500, this is this point here, 500, this is the critical cooling time. And if this cooling time is too short, then you have stresses and cracks finally. So the expert call it T85 time. 800, short word, 500, T8 time. And it means this T8 time has to be higher than the critical value. And of course, you can imagine if you bring in by induction heat, which is wider than only the laser beam, the laser focus, yeah, then you need more time for cooling down because more heat is inside, and then you can increase this T85 time. Yeah. So, and this you can do, of course, by preheating, as it is shown here, but also we investigated if you make a post-heating. Yeah. So after laser welding, of course, you can try to bring heat in to reduce the cooling, yeah, to increase the cooling time. And here you see the diagram how the heat is induced over the width of the seam. Yeah. So just in opposite direction. And of course, it is then you can control this width again by frequency, and of course also by heating time, and to control, let's say, the amount of heat you bring in here to increase the T85 time. So we have applied this meanwhile for a lot of different applications, not only application of thin strips, thin sheets for the car industry, also bigger sheets, bigger thicknesses of sheets, up to 100 millimeters, even for ship buildings, yeah, sometimes 50, 100 millimeters. It also works. And today, of course, classical in Germany is to use it for welding of the big towers for windcraft generators. Yeah, it has to be very strong. Yeah, this offshore windcraft generators, and also you have there 50 to 100 millimeter steel. Yeah, and also this combination laser, arc heating, and induction heating gave a lot of advantages for these applications. Of course, always for research projects, always you have to look for money, yeah, and then you have to have some aim. And if you describe this would increase the stability of this windcraft towers, yes, everybody of course gives money for that. Yeah, if you say this is only for ships, nobody will go give you money. Yes, it's clear. So now I'm coming more or less to the end, but to another topic of EPM, for us, very new here in Russia, and especially in St. Petersburg at the Leti University. You know, this is a classical application of the so-called skull melting. And 10 years ago, we started a cooperation with our colleagues in Leti to bring this technology also to our institute with good success, and still running, of course. So it is oxide and glass processing, I called it. It is a so-called skull melting technology. Yeah? So it's a very interesting process, and I never understood why nobody was interested in this process, let's say, in the last 40 years, because it was invented already in the 60s by Russians, by French people, and by Americans. But I have to say, okay, only the French followed it a little bit, but mainly the colleagues here in Russia followed it. And since 10 years, of course, we also in Hanover took it over. So it's the industrial application, and we are just on the way to realize it in industry, in real industry, is very modern. Yeah. So it's a very interesting process. It can be used for melting of special materials like oxides, glass, and ceramics, which have the property that they are non-conductive or low conductive at room temperature. Yeah? You know, ceramic in electrical engineering, aluminum oxide are well used as an insulator. Yeah? It is a low conductive or non-conductive material at room temperature. Also glass, you know, is not conductive. Yeah? But at high temperatures, it becomes conductive. And this is very interesting, and that makes this principle possible. So imagine that you have, again, a kind of cold crucible, which you know already, but in this application, not for metal, for this kind of materials, like oxides, let's say. You put then oxide in your cold crucible, powder. You switch on your generator, and of course, nothing happened, yeah, because the powder is non-conductive, yeah, no currents induced. But then you heat by some methods this powder up to a higher temperature. For oxides, you need only 2,000 degrees centigrade. Yeah? Then this material becomes conductive. It means it couples to the electromagnetic field. It is directly heated. And a melt starts to be generated. And then this melt comes closer to the cold crucible wall. And of course, it's strongly cooled by the cold crucible. Yeah? And so, at some certain point, the conductivity goes down because it's cooled. Yeah? And you have no more coupling. So it means, finally, you have here a short layer of material, which is non-conductive because it's at low temperature. It's strongly cooled. And this is like a crucible. Yeah? Like a crucible. But the trick is that this material is the same like the melt. And it makes it possible to melt very pure materials. Yeah? And of course, this skull is also then a kind of thermal insulation. It's a good thermal insulator, ceramic, much better than metals. Yeah? And it's, of course, also electrical insulator. Yeah? Because here, it's a cold crucible, you have voltages. Yeah? And the melt is, of course, kind of short circuit. Yeah? So that means you can heat these materials inside this crucible with this method, and this layer, this artificial crucible, is called skull. Yeah? Skull. Yeah? And therefore, the method is called skull melting. So you can reach very high temperatures. I told you in the very beginning, yeah? No limitation of temperature. You only need power. And for example, if you want to melt zirconium oxide, which is very typical, its melting point is 2,700 degrees centigrade. And a little bit overheating, you need more or less 3,000 degrees centigrade. No? And you can really realize it. Of course, you need something for preheating. Yeah? I told you already, okay, imagine it will be hot. If we use glasses, we use a burner, gas burner, because glasses becomes conductive already at 500 degrees centigrade. This is very easily done by a gas burner, yeah, from top. And then you get a kind of bath here. And this bath is coupling, and then the heat goes through the whole melt. But in the case of oxides, the temperatures are too high for gas burners. We use the metal of the oxide. If you want to melt aluminum oxide, you use some pieces of aluminum. You put these aluminum pieces inside the powder. The aluminum is coupling. It is overheating. Heat cannot go away. Yeah? And then it is heating the powder around. Yeah? And so it generates a small area of high temperature, and then it's coupling, and then it is starting. This is a typical starting process. And of course, as I told you, this skull, yeah, protects against impurities. It even makes the melt purer than before, because if there are some impurities, they will stick here on the surface of the skull. Yeah? Very important for glass, for high pure glasses. So the installation we have installed in Hanover more than 10 years ago. We started 2003. It went to operation. It's quite powerful, 320 kilowatt. It uses a thyristor and a transistor generator up to 300 kilohertz, and we have were supported by our partners here later in St. Petersburg, because they had a big knowledge experience in that. Here is a system. This is a chamber. Okay, here inside are the cold crucible. It's not so clear shown. Here's a converter. And this can be closed, of course, for safety and so on. There are some glasses to look in, for pyrometer to measure temperature. Here's a charging device. Yeah, this is also this is a pyrometer. Yeah, and a big water control system to check the energy consumption and the efficiency of the process. Here you see some results. So we have used two kinds of inductors. This is a classical cold crucible system. Yeah, here you see again the cold crucible, a little bit different from the metal applications. It's a little bit more simple. They are tubes, yeah, water-cooled tubes, then bended together. Water is collected here on the bottom, and this is the inductor. This is the cold crucible principle, but we also use the so-called inductor crucible. You see here, this is a one-turn inductor, which is by itself the crucible. Yeah? So we have no separate inductor and crucible. We have only one turn, and this is the crucible. This is a little bit more effective, and we use it specially for glass melting. Here you see it is full of glass, not melted, and then only pieces. So, and here you see some results. This is, you will see just a movie. This is zirconium oxide melt, and this is YBCO, a superconducting material already melting at lower temperature. And here you see the melting of zirconium oxide, temperature 3000 degrees centigrade. Of course, video is done by a filter system. Otherwise, it will be completely white. And you see it is liquid like water at this high temperature. The operator is a little bit nervous here, you see, because 3000 degrees is not so for the first task and something new. And these are then some products coming out. You can generate crystals. Yeah, this is zircon crystals, artificial diamonds. Yeah, this is zirconium oxide. This is the result of glass melting. It is still a little bit green. It should be optical glasses, but finally it really was very pure and white and transparent, of course, for optical applications. So we are just on the way now to bring it to the industrial applications. Company in Hanover is very interested in, and we are nearly to start this real industrial installation, and also together with our colleagues here from St. Petersburg, from Lidi. So, yes, I have maybe 5 minutes because we always also have the chance to ask some questions, and this is the last part. Very shortly, very well known is the EPM in crystal growing, classically for semiconductors, for microelectronics, and also today for photovoltaics, yeah, photovoltaic solar cells. And why to use EPM in the crystallization of or generating of crystals? They are mainly for monocrystals. Yeah, there are typically two processes. One process is so-called Czochralski process. Next slide will show you the principle. It is mainly used for microelectronic circuits. Yeah. Today it generates crystals with a diameter up to 300 millimeters. 450 are in development in the moment. And the length is nearly 2 meters. Yeah. So you use here the pure silicon, then you melt it, then you pull it from the two crystals. I will show you a little bit later. And then finally you have the wafer, and from the wafer you make your microelectronic pieces. Yeah? The principle is shown here. Yeah? Here you have the melt. The melt is held in a quartz crucible and graphite, inside quartz, outside graphite. It is heated. It's not shown here typically by resistance heaters, graphite heaters. And then the crystal is taken from the melt very slowly. Of course, it takes 8 hours for such a crystal, and then also rotated, yeah, to improve the quality. So, and the aim to use electromagnetic fields here, EPM, is to increase the quality, because the temperature distribution and the velocity distribution in this melt, silicon melt, is very important for the quality, for the homogeneity of the quality of the crystal. Yeah? So electromagnetic fields, and here are only shown which possibilities you have. DC fields, which are damping the melt flow. AC fields, which are promoting the melt flow, can be applied and have been investigated. Yeah? And here you see really such a modern crystal, an installation here. The crystal has 300 millimeters, the weight is 300 kilograms. Yeah? It's very interesting. It hangs only at this very thin stick here, 5-6 millimeters in diameter. Yeah, and it's grown by Tucholsky. So, and this electromagnetic fields, mainly today damping DC fields, yeah, leads to the high quality of these materials, because with an increasing diameter, the problems are increasing to get homogeneous crystals. Yeah. So the second process is the so-called floating zone process. Floating zone processes is an inductively heated process. So you have a feed rock, which is polycrystalline. Then it is remelted. Here you have the red is the melting zone. And then it is crystallizing here, and then you have a single crystal. Yeah. So this principle today is running up to 300 millimeters in diameter, that is 8 inch. Yeah? And it is mainly used for power electronics, yeah? Transistors, diodes, thyristors. Yeah? So, and it has a much higher quality like the previous one in Tucholsky, because for power electronics you need, of course, one whole wafer. And if you have one defect inside the wafer, you cannot use it. Yeah? If you have a microelectronics, you have 1,000 circuits on one wafer, and if one is bad, nobody cares about. Yeah? So you'd use the 999. Yeah? Okay, so that means for floating zone gives a much higher quality than Tucholsky, and is therefore used for power electron, but it's more expensive, of course, and I think only 10% are made by floating zone, 90% is made by Tucholsky, because it's cheaper and more simple. So, but also the problem with a floating zone process is that also you need a homogeneous distribution of the quality, and the main factor of the quality is the resistivity. The resistivity must be homogeneous, because if you have not a homogeneous resistivity, finally in your diode, the current will flow there where the lower resistivity is, yeah? And then you have not a homogeneous current distribution, and this means you have a local overheating. So you need a homogeneous resistivity of your wafer, and the resistivity is mainly influenced by the participation of oxygen, yeah, inside the crystal, oxygen distribution. And the oxygen distribution is a question of mixing again. Yeah? So you need a strong mixing here to homogenize the oxidation distribution, and therefore sometimes the mixing only by the inductor is not enough, and therefore you use additional mixing, for example, by this rotating field magnet. Unfortunately, it's in German. Yeah? It's a rotating field magnet, yeah? And it's like a mixer. Yeah? It mixes the melt, and then you can show that with a very small flux density, only 1 millitesla is enough, yeah, to mix the melt, and then you have a very good homogenization of the oxidation distribution. So this is nearly my last slide. This is the use of EPM also in solar cell production. It's a sort of EFG process. It's a process which generates very thin solar cells, so a hollow cylinder, as you can see here. It generates from the melt a hollow cylinder here in reality, yeah, which means that finally you have to cut only the solar cells here from this cylinder, and the thickness is already the original thickness of about 300 micrometers, yeah, 0.3 millimeters. This process was developed and forced when silicon was quite expensive on the market. Today it's no more so interesting because there is a lot of silicon on the market, more than we need in the moment. So silicon is very cheap, and unfortunately, therefore, this process in the moment makes no sense. But nevertheless, we have tried to improve, to optimize this process to a state that it really worked. And I hope that in some years it will come again. So now I come to my conclusions. The use of EPM methods, electromagnetic processing methods, has a grown potential in metal, in non-metal, and also in semiconductor industrial applications. In classical applications like melting, heating, heat treatment, in order to increase the quality of the materials and the production output, maybe also production speed, as I have shown. In the well-known skull melting method for new applications, new technologies, and new materials, you really can generate new materials, nanomaterials, for example. And especially the semiconductor and photovoltaic area offers new potentials for the use of EPM in order to increase the quality, production, and efficiency of the materials, efficiency of solar cells, for example, but also the production, the productivity to decrease the costs of materials for solar cells, which of course is very important. So I'm at the end of my lecture. Thank you in the moment. And of course I'm free for any questions if you have. We still have some minutes, so we are not exactly limited. Are there some questions? Was everything so clear that no questions came up? Okay, if everything was clear, then we can close now this lecture. Thank you very much for participating, and I hope it was interesting for you for different sides of using EPM. It's not so typical, of course, for electrical engineering, but it's an area. It's not well known, not like the area of mobile phones or something, communication, but it's necessary for all directions. I always say without EPM we would have no mobile phone, because you have to generate the crystals of gallium arsenide, for example, fast microelectronic devices, and we cannot drive any cars, and nothing else. So a lot of basic technologies are based on EPM. Therefore, it is so interesting. So thank you very much, and have a nice day. Thank you.